Good morning, everyone, and welcome to the Hydrogen and Fuel Cells Europe Technical Forum here at the Hannover Messe 2023. Please have a seat, have a drink. The hostesses are here to serve you, and the drinks are on the house. We have a very interesting topic coming up for you today. We'll be talking about the aviation and the maritime sector, some sectors that have some very big challenges ahead of them to decarbonize. Please, I would like to welcome to the stage Dr. Asif Ansar. Welcome from the Head of the Department of Energy and System Integration at the DLR. Please give Doctor a round of applause.
Thank you very much. The harder to abate industries are the industries which cannot be abated easily. That's how the definition goes. That means we are talking about reducing the emissions, the CO2 pollutions, but there are some sectors, and two of them, we're trying to do them at DLR, not because they're easy, but because they're hard, right? So utilizing the famous proverb. One of them is aviation, which is directly linked to the German Aerospace Center, the core activity of it. But then there is spin out towards waterborne transport. And the reason is simply because collectively it's about 6.5% of the CO2 emission, but much larger other pollutants, the SOx, NOx, which have a direct effect on the human health. And this is impacted by burning the fuel on the airborne or the waterborne transport. And based on that, there are different programs, the flight path, the EU Green Deal, the CORSIA on the aviation side, or IMO that is coming up for the waterborne transport to reduce these emissions gradually in 2030, 2040, and going to almost a sustainable future or zero emission by 2050, right? So these are the targets we want to achieve, but there are no easy target to it. And in order to reach there, the approach is to, on one hand side, go for more sustainable fuels, but at the parallel, we are working on fuel cell powertrains, both for aviation as well as shipping, though not the same technologies. So when it comes to for the aviation sector, my team has been developing fuel cell and hydrogen, primarily because the majority of emissions comes from the short-range aircrafts. So that means all the aircraft which is flying from Frankfurt to Paris, Frankfurt to Madrid, and those are the central hubs. You see also the traffic, which corresponds to also the NOx pollution, but also corresponds to the most of the CO2s coming up. So per flight, going all the way to LA is probably high intensity of carbon, but since the traffic is lower compared to the original aircraft, we can directly address it by utilizing hydrogen. So this area of traffic, which you see is the large areas, our target is to put in 70 to 200 passengers aircraft, traveling up to 1,500 kilometers with fuel cells powered by pure hydrogen, right? And for the area which is beyond that, the distance or the passenger's capacity, which is bigger than that, we still want to continue utilizing the kerosene, but this time it will not be a kerosene from the fossil sources, but we are generating our own projects on e-kerosene at that time. All right. And why hydrogen and the fuel cells? Because even if you're utilizing the e-kerosene, the net carbon will go down. But other pollutants, again, the SOx, NOx, and that are produced, and black particles continue to remain the same, right? So it is not just about, so we should not be, when talk about the sustainability, we should not get a tunnel vision about the CO2. So CO2 and other pollutants both have to be reduced hand in hand, and hydrogen and the fuel cells is the only viable technology to attain that. So we have a vision of going towards a short-haul aircrafts that we will fly or we want to fly with hydrogen and fuel cell. But we already did that. So we already had aircraft, a 2-passenger aircraft and a 4-passenger aircraft that we flew with hydrogen and fuel cell, a gaseous hydrogen. And right now we are running a project which is called 328 H2FC, where we're integrating a 1.5 megawatt fuel cell and hydrogen for 70 passengers. And at the same time, we are doing a project Bali that I will be presenting, which is the ground testing, qualification, and validation of all the components that we will be installing in this aircraft. All right. So our very first attempt of hydrogen fuel cell is back in 2009 with an aircraft called Antares, a 2-passenger aircraft. Then High 4, which is in 2016, took off and landed from Stuttgart and also in Hamburg. And now this is up to 4 passengers, can already reach 1,500 kilometers at a speed of 200 kilometers an hour. Now the target is that we mimic this kind of performance in a 3 to 8 aircraft with the 70 passengers, right? To do that, we start from very much from the concepting, from the design of it, which also allow us that where the integration will happen. So instead of using right now the 3 to 8 because of the IP challenges, I'm showing a typical aircraft that DLR own is designing and how the fuel cells will be divided all over with the heating system, the supply of hydrogen, so on and so forth. After the designing of these, we also go on the sizing of the components, so very extensive modeling tools that allow us the sizing from the stack to the cooling system, but also with the different missions. And also there are two possibilities, a high efficiency design versus a lightweight designs. And these can change the sizing of the component. In the sizing of the components, one of the key element is the weight budgeting, right? So that weight budgeting has to come in. Today, we are at around 0.5 kilowatt per kg as a system weight, and this needs to almost increase by 4 times over development. And this is a call for all the fuel cell developers as well to come along and help us in developing there. All right. After these analysis and the sizing, this is our Bali's project that I already mentioned. 40 kilometers down of the Stuttgart, we have acquired this land, and the different areas where the fuel cells, the motors, the cooling systems, the control switch systems, all been installed, 1.5 megawatt. This is not a finished iron bird or a powertrain, but these are individual components spread over. Each and every will be tested, qualified as per the certification and the requirement of the aviation. And eventually, when the testing will be done, the idea is that these will be converted into an iron bird, and that iron bird will afterwards will be installed in a 3 to 8 aircraft. Behind here, instead of using the gaseous hydrogen, we have moved towards the liquid hydrogen. And liquid hydrogen tanks will be coming in here. There are 2 types of tank system. One is that will be go into the aircraft, almost 200 kgs. Right now, we have only available, which is 50 kg available. And on the back end, we are also putting a liquid hydrogen tank, mimicking the tank that will be at airport, almost 2.5 tons of the liquid hydrogen that will be stored. And how the transfers will happen, that is itself a challenge that we are trying to look at it closely. The last project activity on this is then a real demonstrator project, 3 to 8 project, where we are upscaling of the fuel cell, bringing it into a more closer iron bird. And that will be a multiple system, not a single 1.5 megawatt, because of the redundancy and safety. We will have multiple system that will be on the back end, and the hydrogen tank will be also installed. Everything will be entered through this back door, and installation will happen on the back side of it. So with this, our aim is already to have a demonstration in the next 3 years. We want to fly with it with all the certification. And 2035, with our partner, Deutsche Aircraft, we want to go towards a commercial first class of aircraft to fly passengers with. All right. Now, a similar challenge, but this time on the shipping industry. And there we are working also with some of the companies in order to solve the problem towards pollutions on the shipping side. But we are not using any more hydrogen. And the challenge is majority of emissions, unlike in aircraft, where majority of emissions come from the short-range aircraft, in shipping, majority of emissions come from the long-haul ships, whether that's cargo ships or passenger ships. That means with the challenge is that with the hydrogen, we have a very low energy density. Similar issue that if we cannot today fly all the way to LA with hydrogen, but the hydrogen fuel cell is a solution for aircrafts today because of the short range issues, here hydrogen will not be able to utilize. So our suggestion is that we are going for a liquefied natural gas. But you will say, but then how you're cutting off the carbon emission, and I get it, right? So one of this reduction is happening by power efficiency because of using fuel cells as a powertrain. But more importantly, we are already working on replacing the natural gas with synthetic methane and liquefying that. So 2 projects running on. In the H2 Mare project, the Explore, you will look into it. We have a high temperature solid oxide electrolyzer, which is a co-electrolyzer unit, takes the CO2 from air, and the water is coming from the sea. and that is converted into carbon monoxide and hydrogen under pressure, and because of pressurization, we are converting it directly into methane. And that methane is then liquefied to go for the shipping, but at the same time, a process we call it power bio to gas. So the biogas, which has a high amount of carbon, residual carbon, we're taking the methane from the biogas, and the carbon is converted again into methane and make it PBT gas, and this will be power as well as biosources of it, and the methane will be formed that is then further liquefied for utilization in the shipping side of it. But the technology, therefore, we are using is not the PEM technology, which because we are not using hydrogen as a fuel, rather than we are using high-temperature fuel cells, which is much more suitable and have a much higher efficiency than coming up when LNG or natural or liquefied synthetic methane is utilized. We're looking at an electrical efficiency of 67%, that is first design has shown. But ultimate aim is to have a decrease of CO2 by 40% and the pollutants as low as 99% compared to the reference point that is coming into it. This is an illustration. Because of the transient behaviors, the fuel cell, the high temperature fuel cell as a powertrain has a poor transient response that needs some time to change. So we are coupling it with the batteries to take care of, not for the peaking of the of peak power, because then we will need a very large batteries. It's only to support the transient behavior of solid oxide fuel cells. One of the proof of concept in the Stuttgart, you are welcome to come and see that in our laboratories. It's a very small unit, only a 30 kilowatt unit. A single unit will be roughly 300 kilowatt that we will be putting up, and many of these 300 kilowatts will be installed in an engine room next to each other to get to a 3.5 megawatt to 3.9 megawatt, and this will eventually power a 40 megawatt requirement of a ship. First testing of it, we already shown initial efficiency in the range of the 60%, but now with the further improvement, we are wanting to show that a 67% efficiency and the transient behavior can be shown. We will have a more detailed coming up in upcoming project, but you're welcome to come and see us at our booth, D13, as well as 8534, and we will be happy to talk about it. With that, I conclude, and I hope that I will be able to show with the fuel cells, PEM powertrain, as well as solid oxide fuels powertrain, aviation, and the shipping industry could be moved forward towards decarbonization with the choice of the right kind of a fuel. Thank you very much.
Thank you, Dr. Ansar. Are there any questions from the audience at the moment? Then maybe I have a very interesting question. So I think a lot of the people here, they probably came into Hanover by airplane. Now they're using fossil fuels, they're using kerosene. Roughly, what year do you think we'll be flying on hydrogen? I know this is a difficult one, but maybe you have some insight.
Yeah, so 2035 is a target when we want to have a first commercial aircraft together with our industrial partner. But at the same time, we have a parallel project that I did not talk about it, is about the e-kerosene projects, where we are already trying to go up to 20% of blending of the fossil kerosene with our e-kerosene. And we hope, and we're working with the EU policy, that this target needs to be further strengthened up, that on one side, the e-kerosene could, for the long-haul aircraft, could be increased, and by 2035, while we develop a hydrogen aircraft for flying or the short ranges.
It's good to hear that you're working on decarbonization, these industries on multiple routes. Thank you very much for your presentation. Please give Dr. Ansar a round of applause.
Thank you.